our individual who is out of the classroom right now gets the lesson. And let's get started. So databases are containers. They are containers for tables. And so up next, we're going to talk about tables. They are the citizens of databases. And that's data can't live in at least in a database. Data can only live on a table. Tables can only live in databases. And databases are what live on a database server, right? So when we talk about tables, database tables, we're talking about data that is in a table format. And when I talk about data being tabular or data being in a table format, it means rows and columns. Columns are each individual value, like name, rank, serial number. Each row is a specific observation, right? Each row is a single observation. Tables have visually a lot in common with spreadsheets, right? So think of tables as big, huge honkin' spreadsheets. And there's a couple of things that are different about a database table versus a spreadsheet. And the first difference is going to be in the size that a table can hold. Tables can hold millions and millions and millions of rows. Also, another difference is that MySQL has something called a data type. And in spreadsheet applications, we may have formats for data, but we don't have strict data types. If you have a column that's numeric, you can also, or a column that mostly has numbers, in a spreadsheet, you could put strings inside of there too. SQL is not going to be so forgiving, so it's strict on the data types. We're going to talk about how to create tables, how to show tables, show what's on them, describe tables, and dropping tables is pretty destructive as well. That's in case we need to nuke a table. We're also going to talk about this concept called a primary key. And a primary key is a unique identifier for a row on a table. That's the short example. And then there's a bit in here about using external SQL scripts. We're gonna skip that one for right now. Okay, so our data lives in tables, and our tables live in databases, and our databases live on a database server. So big deal. Unlike spreadsheets, database tables have a hard set of columns, and it's up to developers and database administrators and data scientists, whoever, data engineers, to make sure that we define those columns explicitly, and we define explicitly what kind of data type that they can hold. This is a big difference, right? Excel and other spreadsheet applications, they're very, very popular in business. However, the reason why databases are popular in software and in data management is that things aren't quite as loosey-goosey, right? You can't just throw on a new column or without a major change to a database. And the reason why this is the following term: data integrity. Data integrity. You don't have any guarantees of data integrity on a spreadsheet. You do have guarantees of data integrity on a relational database table. And the first place that comes through is what columns we have. Right, when we look at a specific database, like this fruits database, on this, the only table inside of here is the fruits table. This table, we can't just add on more columns here. I mean, we can if we modify the table, but that's a major undertaking to modify an existing table. And if you modify existing tables that an application is running on, you might cause some problems, right? So that's kind of a big deal. So the column names as well as the column data types are critical, and they help us have data that conforms. If we have data that conforms to a certain shape and expectations, we have more data integrity. There's that word, integrity, right? So let's talk about these data types. MySQL and most of our database systems out there are what are called statically typed. That means that once we make a column that holds numbers, it's only going to hold numbers. Once we make a column that holds decimals, it'll only hold decimals. When we make a column that holds strings, it'll only hold strings, right? And we need to specify this beforehand. Y'all will be creating some tables a little bit later. For now, we're just going to work with pre-built tables. And let's take a look at some of our data types. There are a variety of numeric data types. There's not such a thing as just a number data type in MySQL. There are various kinds of numbers. And let's talk about this. Int is, I'll give you a crazy guess. Int is short for integer, right? You've seen integer before in some of your pre-work, I'm sure. All it means is a whole number positive or negative. And when we look at integers, there are actually two types of integers in MySQL. We can have an unsigned integer, which means that we only have positive values. Unsigned means there's no sign, like positive sign or negative sign. If we add unsigned, we can only have positive values. If we don't have unsigned, if it doesn't exist in a column's description, then that value could be positive or negative. Why does this exist, and why would we want to have only positive numbers in some places? Well, there's that term again, data integrity, right? If we want to have data integrity on something like the quantity of fruits, right, then we need to make sure that this is an unsigned integer, right? What if we were checking, what if we needed to track positive and negative, like inflows and outflows, right? Like quantity of fruits that somebody owes us might be negative too, as opposed to inventory, right? So there's not a one size fits all answer. It really depends on the scenario, right? But you can enforce this integrity. If I take a look at this structure, I see that this int does not have any modification. So we could have a negative quantity here, technically. Heather, a question. Go ahead.
Do ints and unsigned ints have a limit?
Yes.
Like how high they can go?
Yeah, let's check it out. I'm going to click the link to the docs right here. And let's see, something's up with the link. No big deal. Reference. Data types, numeric data types. Let's find that for you. Ints, here we go. An integer that is signed has a minimum value of 2.14 billion, positive value of 2.14 billion. And if we have an unsigned, meaning positive only, that number doubles. So we go to, I'm pretty sure that's billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. Yeah, 4.2 billion. So if we know ahead of time that we're going to store a value greater than 4 billion, instead of integer, we should use big int for a big integer. And you'll notice that this is the different sized numbers and the different sized number data types. See how this tiny int here, tiny int goes from negative 128 to 127, or we could make it positive only, and we get that same exact number of possibilities. But see how a tiny int is 1 byte worth of storage, which means it's more efficient. It's taking up less space. It reads faster, writes faster, processes faster. A big int is 8 times as large, right? So we want to reserve a big int for things that need a big int. And if we have a value that's only going to go as high as 127, then we'll keep that a tiny int. And then we have a more efficient, not just data integrity, but we have data read and write optimization on the database because we're not wasting resources. Yeah. So I'll share that link in case you need it. There's also, let's see, I'll put that in chat in case you'll need it. Cool. Emmanuel, question. Go ahead.
This might be obviously a topic that is a little bit outside of what we're trying to learn today, but you talk about this data integrity. Obviously, when we're more advanced in our data careers, we're probably going to have to mind that aspect, right? So, like, ultimately, it depends on the data engineer and how they define these columns, right? Is that or is that automatically some sort of magical computer thing?
No, there's no magical computer thing. There's human beings who have to think about things and plan things and ask themselves questions. If I'm storing an integer, will I ever go above 4 billion? If I do, I need to use a big int. Am I ever going to have a decimal? If I'm going to have a decimal, we don't use int, we use float, right? But do I need to store money? I use a decimal instead of a float, right? Because there's rounding errors in floats. So we don't use floats for money, we use decimals for money. So yeah, it takes planning. It takes interrogating the real issue. And this is the domain of database administrators, software developers, data engineers. You know, in your first role, I don't think y'all should be setting up databases from scratch, but rather connecting to existing data stores. But yeah, hope that answered your question, Emmanuel. Awesome. Tyler, go ahead.
Cool, thank you. I get, you know, when you're saying that we're not going to add an additional column, that we'd be better served just generating a whole new table. But what about adding a row?
Oh, adding a row is just inserting records. That's what
Right.
tables are for, is holding new records. Like for example, I'm going to go in here and I'm going to make a new, I'm going to make a new fruit in here, and we'll call it pineapple. Right, we'll add pineapple, and we'll say that we have 20 pineapples. Right, in what we're up to, we're doing more reading than writing, but applications will be writing to databases usually, right? Pieces of software. And when when we get new users, like when I made y'all's user accounts, those were insertions into the table. Yeah, that's normal. Modifying a table, that's surgery, right? Adding or removing columns or changing column data types is surgery, is database surgery. But adding new rows is just adding new rows. Does that help? Awesome. Cool. Ints, there's various kinds of ints. Floats have decimal values, but there can be some rounding errors if you're dealing with money. And just like how we have different sized ints, we have different sized floats. Floats can hold pretty large numbers. Doubles can hold double the size of a float. And if I look for the docs here, and I look in 5.7, data types, numeric data types, and I go to float and double, what we see here is that a float and double represent approximate numeric types. MySQL uses 4 bytes for single precision, which is float, and 8 bytes for a double. And 8 bytes is a lot. 8 bytes is a lot of storage for one number. So that's pretty high. Yeah. We don't use floats, however, with dollars and cents because of rounding errors. For anything where we need to have a nice proper rounding, especially like in money, you'll use a decimal data type. And in there, we'll specify the length, like the overall length of the number of numerals. And then we follow that with the precision to the right of the decimal. So in this example, decimal 4,2, this allows 4 digits total with 2 of those digits to the right of the decimal, okay? And decimal columns are built for storing money. Floats will, if you've seen the movie Office Space, part of their hack in Office Space is making use of a rounding error. That rounding error was because somebody at that company stored money in a float instead of a decimal. That's how they were able to run that hack, right? So it's just floats can get approximate, but if you want a precise decimal, use a decimal. Okay. Yeah, like Superman 3, that one as well. True story. All right, we talked about signed versus unsigned. If if you know ahead of time that you will never have a negative number, use unsigned. And I'll give you a perfect example of that. ID columns, actually, I did make the quantity negative here, or unsigned, so that the quantity can only be positive. Hey, look at me go, I love it. So if I try to make this negative 200 or negative 230, I'm going to get an error. And that error is I can't save it, out of range value, right? So I'm enforcing integrity. Another spot where, I'm going to discard those changes. Another spot where we will always have positive numbers is unique identifiers. We don't have a concept of a unique identifier being negative. So those are always going to be unsigned. Okay. In MySQL is a little funky compared to some of our other flavors of SQL. We don't have a Boolean data type, if you can believe it. It's kind of weird. Booleans are trues and falses. And the way that we would handle a Boolean in MySQL is with a tiny int data type, so that we're only using the 1 byte of storage, not any more or less. And I'll give you an example of that with Titanic, a nice gruesome example in Titanic. When we look at our passengers and we look at the content, we don't see ones and zeros. We don't see trues and falses if they survived, but we see ones and zeros. So if they survived, they're a 1. If they're toast, they're a 0, unsurvived. So those aren't actually Boolean data types with trues and falses. They're zeros and ones. It's just a quirk of MySQL. Pressing forward, we also have string types, and the same kind of logic applies for data integrity on string types. The three most common, the 3 string types that you're going to see are char, which is short for character. And this is really, really short. This is where our length is 1 character to 255 characters. This would be good for a zip code or a phone number. And I'm suggesting that and I'm not suggesting, I'm telling you straight up right now, we use string types to store phone numbers, and we use string types to store zip codes. This is because we don't do math on phone numbers, like arithmetic on phone numbers. Also, if the highest possible positive int is 4,294,000, what happens if you have a Houston area code or a Bernie area code, right? We have challenges here. So phone numbers are not actually numeric data types, and nor should they be. We should store phone numbers in string types. Character is really good. This will max out at 255. If we're going to use, and we know that we're going to use more than 255, varchar or varchar is a bit more common. Varchar length can go up to 65,000 something characters. And that's quite a bit. But it's not a book, right? A varchar might be fine for a title or an article, or maybe not even an article. It kind of depends. But varchar is good for first names, last names. Char would be good for like city and state names because it's shorter. I mean, somebody's full name may be longer than 255 characters, so you don't want to limit things. Email addresses are stored in varchar, same thing with passwords or varchar. And if you need a huge block of text, like potentially a book or an entire library, text is the data type. And the text can be of any length. And I know it might be really tempting to use text for everything, but it's using the most memory possible. So for things like zip codes and phone numbers, we might need a nice shorter string like a char. For most text data, that comes in a varchar or a char. But text is there if you need a huge amount of text. Okay. Looking at, I got a question in chat about are tweets chars? Probably, yeah. Yeah, in fact, the character limit of Twitter being 140 characters, they probably had that set to 140 in their char for the tweet length for a long time. And then they made a big deal out of doubling the length recently. Yeah. Okay. Questions on string types so far? Anything coming up for y'all? Oh, Xavier's got a good one. Our char is a fixed length through. You can go up to, so for saving something in a char with a specified length, your entry can go up to and including that limit, but you can't go past the limit. So like we could have a char of 255 for first name. And if I put my first name RYN, I'm not using all of it, but I'm using just some of that, right? Yeah, good question, Xavier. There are date types, and I'm not talking about blind dates or double dates. I'm talking about time, right? And with the date types here, we have a whole bunch of different types, and there's a link to the documentation. There's more than these three. What's very, very common is a date data type is the year, month, day. And these are database defaults. You might notice in Europe, people write the dates one way. In America, people write the dates another way. In the military, people write the dates a third way. It's because everybody thinks that they have dates figured out, which is actually not a true statement. Nobody has dates figured out. If we had dates figured out, we'd use the same format across the planet, right? But we don't. But that's year, month, day is the default. So you might notice somebody's kind of databasey if they do your year, month, day in that order. Time is down to the seconds. And if you do date time, it's hour, year, month, day, hour, minute, second. And we can get into finer grained time representations than seconds all day long. We usually don't need to. But if you ever run into that, check out the docs for whatever version of SQL and whatever flavor of SQL you're running, and you'll get the data types, like in case you needed to count nanoseconds for some reason. Cool. Let's see. Let's keep going. There is a value in MySQL called a null, and a null means an absence of a value. So nulls are not a data type in and of themselves. Nulls are saying there's nothing here, no I nada, there's nothing here. There's an absence of value, right? We have the data type none in Python is the same thing as null in SQL. And because null is representing an absence of value, we can't ask questions like if null is not equal to null or if the null is equal to null. That's nonsense. That's like asking if one black hole is the same thing as another black hole. I don't know, there's nothing there, right? So it's the presence of nothing or the absence of value. Where we see nulls is not, we don't just make a column that contains nulls. What we do have though, is we have columns, and I'm looking at Titanic here, nice and gruesome, right? And we have the structure of the data types. So we have some big ints for some of these. We have text, and this is kind of silly. We have text for the gender column, which is not optimized for memory, right? But we see that some of these columns allow nulls. Are y'all seeing that in here? Some of these where the default is null, and the checkboxes in here as well are allowing null or not. So if we allow nulls, that means we allow holes in our data. We might want that in some cases. We might want to protect against that in other cases. So I'll give you an example in the employees database. Here's a good one. Let's look at the salaries table. On the salaries table, we have the employees number, and see how this one employee has had a whole bunch of different salaries across time, hopefully going the right direction. So one employee is represented by their employee number. They have the salary. The from date and the to date are date types. And let's take a look at the data types. The employee's number is an integer. The salary is an integer because we're not dealing with decimals here. It's nice round full dollars. But notice we have the date data type for from and to. Are we allowing nulls in here? No. And this means that we are purposefully saying, if you try to save something to the salaries table with a missing value, you will not be able to successfully save that. It's kind of similar to how we can't make a commit with a commit message. It just does, that operation fails if you don't have a commit message. The commit aborts, right? It terminates. Some places we might want nulls, right? Like Titanic is a really good example. We can't be pushy with the Titanic data and tell them we don't accept null values. Like the data is the data, and this individual here, we just don't know how old this individual is. The data wasn't in the records. So we want to keep this row that represents this individual who is passenger ID 5, who perished, who was in 3rd class, and they were traveling alone. We need all this other information, but we're tolerant. We're tolerating the nulls in the data here. So there's a judgment call. Some places you will find that a table is tolerating nulls, or a column. It's not just a table, but because this is by column. Some columns allow nulls, some columns don't allow nulls. And as much as we want to avoid holes in our data and Swiss cheese data, sometimes we have to be able to handle null values for scenarios like this, when the historical record doesn't have an entry for these individuals, for their name, for their age, right? We just have to tolerate that null and handle it a little differently later. So null itself is a modifier on a column. So I've gone through the introduction to data types and ways of modifying those data types, like the length of strings or the length of floats and decimals. And we can also modify columns by specifying if they accept nulls or not. If you know ahead of time, and this is part of like database design practices, if you know ahead of time that your data is going to have a bunch of holes in it, allow nulls, right? If you're building a table for something and you know that you should only have records that are full and complete, like we don't want to give a, I don't know, if we're running the IRS's backend and their database, we don't want to accept nulls for like somebody's bank account number if we're going to send them a stimulus check or something like that, right? We need that data. So it's a case-by-case basis is the answer for if we allow nulls or not. I'm going to pause here a little bit. I've covered a lot of ground. I'm going to pause and give you all a chance to ask any questions about allowing nulls or not, date types. There are more date types than we cover here. String types, numeric types. Any questions so far before we go into new material?
For most of this data in the beginning, like you mentioned, in the beginning of our careers,
yeah,
we're just going to be concerned about how to identify it rather than how to structure it, like, you know, how to create this database or these columns and all that, right?
Yeah. Ideally, you're rolling into environments where these questions have already been asked and answered. But I need y'all to know the lay of the land, right? And we need to be able to tell nice and quick if certain columns are allowing nulls or not, right? Or what kind of data types there are. Looking at this Titanic, the database geek in me is spazzing out about these big ints when we don't need big ints. It's spazzing out about the text where we only need a char. The tiny int for the alone is a tiny int. But survived is just a yes or a no, so that should be a tiny int as well. So you can get away with a lot. You can get away with putting too many resources but it'll catch up with you over time if we have millions and millions and millions of rows, right? A big int is 8 times as large as a tiny int. And that's a big deal when we're talking about millions of rows. So, but yeah, my take home for y'all, or my takeaway for y'all is we need to make sure that y'all understand the structure of existing tables. And I'm going to show you how to create tables here, but like we're not setting up to be database administrators, right? Cool. Good question, Emmanuel. Thank you for asking that. Creating tables is pretty straightforward. I'll show you the general pattern. And then I'll get into the specifics. The general pattern is create space table name, followed by parentheses and a list of all of the columns that we want to create, followed by their data type, followed by any modifiers and a comma. So if we were to run the create table name, we write the name of the column, followed by the data type, followed by any modifiers, and then a comma. Second column name, space, the data type, any modifiers, comma. So when we look at this quotes example, this is a bit more concrete. In this concrete example, we're creating a table called quotes. There is an author first name that is varchar up to 50 characters, which seems kind of low, right? I'd probably make that a little higher because some folks have 2 first names that they put in their first name. Some people just have long names, right? The author last name, this is a varchar, and we are specifying, not allowing, we are saying no nulls in the last name. So we're allowing nulls on the first name. We're saying no nulls on the last name, no nulls on the content of this quote. So if Madonna comes in here and Madonna wants to make a quote, she'll have to put her last name as Madonna right there because it's not null, it's not accepting nulls. Same thing with share, right? The content here is text, and because we're going for data integrity, we're not allowing people to make null quotes. They have to have some quote if we're going to add their quote to our quotes table, right? Okay, and let's see. I'll show you, we actually have a quotes database in here. And on this quotes database, we have one table for authors, which lists out all the authors. This is a different structure. And when we look at the structure, we see ID as a unique identifier. We also see that the first name we're allowing nulls on, but the last name has to be there, right? The quotes table itself has the content quote, or the content is the quote itself. The ID is the unique identifier for that specific quote. And then the author ID is the ID of the person who's on the author table, who is the author. So when we see author ID of 1 here, 1, 2, 3, all 3 of these quotes here belong to the same author. Y'all see that? Where the author ID is 1, so time is a little illusion, lunchtime doubly so, don't panic. Those are all coming from author ID 1. And I'll talk about this again in more depth, but when we look at our structure, we see our tables and our modifiers, right? Something that's very critical for us and that will speed up our queries is this concept of a primary key. Now, a primary key is a unique identifier for finding an entire row of data. So let's take a look at the employees database. And specifically, we'll look at the employees table, which is a list of all the employees. We have 300, just shy of 300,000 employees here. Across the rest of the entire database, every other table here, we don't need to refer to Georgie Faseo, gender M, hire date 1986, 06, 26. We don't need this entire row full of information on Georgie Faseo, when Georgie's birth date was, anything else in other parts of the database. when we look at this primary key, this employee number, this is a unique identifier, we can go over to the salaries table and we know that same employee number, Georgie Faseo, has had 17 different salaries across time at this company. So by being able to refer to another table's entire row by the key, we're reducing the amount of computation that's going on in the SQL server, which means we're getting faster results, our queries are running quicker, and we're reducing duplication, which whenever you reduce duplication and make things faster, you're talking data integrity, right? You're talking benefits of data integrity.
Ryan?
Yes.
He has a date in there, January 1st, 9,999.
Uh-huh.
And is that like, I mean, the future, or like a default value for like the present day? Or?
Yeah, this isn't some sort of part of the union negotiating tactics to have these roles until the year 9000. In this particular database, this year in the future is how we're specifying that they currently have that salary. Yeah.
Okay, thanks.
Uh-huh. Yeah, that was a good question. Natasha, I think your hand was up. Tyler, I'm not sure if you had a follow-up question from before. Okay, Natasha, go ahead.
Okay, yes. So would you be able to like merge two or no?
Yes.
Okay.
Yeah, you are seeing the future, Natasha. Your pattern recognition, gold star. Because
That was me with that 9,099, Heather. I put that in there, the future.
Yeah, we're gonna stitch all this data together, doing something called joins. This is really kind of the beating heart of a relational database. We don't duplicate data everywhere. We relate data everywhere through keys, which is how we stitch stuff together from different tables. Yeah, joins are really cool. Looking at what we call a primary key, those are unique and they can never be null. Otherwise, it's not a key. And the idea is we generally want one primary key per table. So let's take a look at the SQL that generates this table. Create table quotes. Okay, we're creating a table called quotes. We make a column called ID that is an integer that is unsigned. That means positive numbers only, which makes sense. We don't want identifiers that are negative. We don't want user number -12. We want user number 12. We are not allowing nulls because we don't want Swiss cheese in our primary key. And this auto increment here is saying, hey, MySQL, you handle the numbering things and the counting things. I just want to insert records and you sort it out. Okay. The first name is an optional 50-character first name. The last name is a required, not null means required, right? Content is required. And then at the very end of the table creation syntax, we are specifying that the primary key is the ID column. So we're saying that if we want to refer to an entire row by one identifier, that identifier is the ID column. Question, Miriam, go ahead.
Yeah, and so for int, if we don't specify that it's unsigned, does it default to unsigned?
Yeah, no, it defaults to signed.
Okay.
Yeah, we have to say, if we know that an integer will only be positive numbers, we add the keyword unsigned. If it's positive, negative, and we don't care either way, like it could be like a balance or something like that, then we just don't put unsigned there. Yeah. So you will see, I'm going to show y'all a little example. I'm going to go over to that fruits database. I know I'm kind of hopping around our database here. You'll remember when I made the pineapple entry, I didn't specify the ID. MySQL did that for me because the ID is the primary key. It's unsigned and it's auto incrementing. Right. So again, we're not creating a lot of tables. In fact, we will create tables in the future in MySQL, but we will make tables out of our queries so that we can kind of have like variables later. It's a little different than building tables from scratch. But let's see, I'm going to zoom out a little bit and let's keep going. Okay, cool. If we want to see what tables exist on a given database, the command is show tables, show space tables, no parentheses or anything. And so if we say, show the current database is select database parens. So we see that we have FruitsDB selected, and then we can show the current or the tables contained in the currently selected database. This is going to be show tables, not select, but show tables. Just kind of like how we did show databases. Okay. If we change what database we're using, if we then say use employees and then show tables, and we run both of these in order, we switch to the employees database with the first one, with the first statement, and then we get a table listing. And notice how the output for the show tables command is the same output as the little viewer right here. In fact, this previewer inside of SQL Pro actually ran show tables underneath the hood before it loaded that content. We can get a little more information about tables and their characteristics with the command describe, and then the table name, or the query rather, describe table name. So we can describe, we'll describe, let's say, the employees table. And this is the same information, this describe here is the same information that's contained in the structure button when we highlight a table and click on structure. So we see the column name, also called the field, the data type, and any modifiers on the data type, if we are allowing nulls, and if we have any primary keys or not. And so describe is the programmatic way, because not everything is graphically based. It's the programmatic way of doing if we clicked on employees and then went to structure. See how those are the same. There's a little bit more information in structure here.
Ryan, on the left-hand side where it says tables and views, is there a reason why one is blue and the other ones are orange? Or I don't know if that's just mine.
The yellow ones are tables. The blue ones are like a view.
Okay.
We're not going to get into that. We're not going to use these blue ones in exercises and stuff.
Okay, cool.
Yeah. Cool. Also, so we can click on a table itself graphically and click on structure. This is the same thing as describe table. We can also go to table info, and we get all of the SQL that it took to create that table. So we get the table name in backticks. Don't freak out when we see backticks. We see column name, data type and modifier, column name, data type, any modifiers, data type, date, not null. There's something new that this is sharing here, the enum. And enum is if you had a set of options that you wanted for strings, you could put a set of options in an enum. It's short for an enumeration. So if we wanted like a stoplight, we would do an enum for red, green, and yellow, right? And we couldn't have any values other than that. So like structurally, this particular table is enforcing a binary on this column just because of the enum is forcing a one or the other, and we don't have nulls, right? So not terribly inclusive, right? But enums are a way that we can make a set of options. Okay. Let's take a look at some other tables here. I'm looking at titles. The title the titles table, it lists out employee numbers, their title, when they started, that specific title, when that title is running until, and if it runs until the year 9000, it's because they currently have that title. And then we're seeing something on this primary key that's kind of new. Instead of a single column being a primary key, we have something that's called a composite here. And so the composite is that employee's number put together with their title, put together with the from date, ends up being unique. And this is because the one employee has multiple titles over time. So we can't just use the employee number as the unique identifier. The unique identifier is employee number plus the title plus the from date in this given case. Okay, you'll see composites in a couple of places. This is what's called a composite key, and that's because once we combine employee number and title and from date, then we have a unique identifier. So you might see composites as your primary key. And this constraint here, I'll go a little bit further into this. This constraint is modifying the column called employee number. So this is saying that the employee number on the titles table has to reference the employees table employee number. And so this constraint is saying, if you try and put somebody in the titles table, or the salaries table is similar, if you try and give somebody a salary, but their employee number doesn't exist on the employees table, we can't save the record, right? You can't take the mob boss's nephew and put that mob boss's nephew on the salaries table unless they have an employee number on the employees table. And that's what that, and I'll go to salaries, we'll see that same constraint. Just like with titles, you can't make a title for somebody unless their employee number exists on employees. Same constraint. You can't give somebody a new salary in this data schema, this database schema, unless their employee number exists on the employees table. So no mob boss nephews getting paid unless we actually have them going through HR properly. Christopher, go ahead. Question.
Yeah, so in the curriculum, it says that a primary key, each value must be unique. But how does that work when, like, for example, in salaries, like there's multiple of the same?
Yeah, so here's the deal with, and I'm really glad you asked that, because on salaries, this employee number 10,001, well, this person has 17 different salaries across their history with a company, right? So the employee number in this case is not the primary key. The primary key we can see in the table info is a combination of their employee number and their starting date receiving that salary. So if you take those two things together, it's a unique identifier, and that's called a composite key.
Okay, thanks.
Mm-hmm. Similarly, when we look at the department managers table, let's take a look at department managers. Department manager has the employee number of the manager for that department. So this is the employee number is referencing employees. The department number is referencing the departments table. So we get to see what individual was in charge of what department from when to when. And the primary keys on here are going to be a composite, because we won't have, at least in the structure of this data, one person can't manage multiple departments at the same time. Only one person can manage that department. So we'll have a composite key there as well. Yeah, good question. Good question. The SQL command show create tables, and then the table name. This is programmatic SQL that does the same thing as looking at the table info. So we can do the following and prove it. I can come down here and say use them. We'll make sure that I'm using database, the right database. So we'll select database, show me what I'm currently using, should be employees. Okay. And then let's use salaries for example, for instance, we'll do show create salaries. And the command is show create table name. show create table followed by the table name. Show create table name. And when we run this, see how we get, I know it's kind of crunched up in here, but this is all the same information that we were getting from that table info. It's crunched up. We've got backticks around things. We've got new paragraph entries, but it's the same raw data here. I got a private message. Can a primary key be within a range? No, not specifying ranges. Primary keys are unique identifiers, right? Yeah, primary keys are unique identifiers. And if we have a table where there's not a unique identifier, like salaries, then our primary key will most likely be a composite. Because once we put together a starting date and an employee number, that's unique. Miriam, go ahead.
So when we have these primary keys and they're composite, how do we know, like before we have the data, when we're creating the table, that these keys are going to be unique? Like, how do we know the from date is going to be unique when we are assigning these primary keys?
Yeah, planning is the answer to your question. You think about it, you talk about the problem, you look at what kind of data you've got, where it's coming from. Looking at the salaries, this composite, I think this composite should make sense. An employee may have multiple salaries, but the employee number along with their from date tells you when they had a specific salary for how long and who it was for. So when we look at the structure of the data, if you take the from date, 1986, 06, 26, that's not unique. Somebody else could have that same from date, right? But you take the from date and you put it together with the employee number, you have something unique. You have a unique identifier then, right? None of the other duplicate entries for the same Georgie here are going to have the same from date. If somebody else has the same from date for their salary, they won't have the same employee number. So it takes thinking about it and planning it out. This is the domain of software developers, database administrators, planning this out and talking about, okay, what are the data? What's the data going to look like coming in? Will one person ever have two different salaries at the same time? I mean, you kind of have to ask the questions because the SQL table doesn't care, right? It'll do whatever you need it to, but you just have to tell it what you need, right? Did that answer your question, Miriam?
Yeah, and can this be like changed later on after creating the table, or no?
You can. It's database surgery, but you can change it.
Okay, but not ideal.
Not ideal. Not ideal.
Thank you.
That's why like adding features to web applications takes time, because you might have to like change the structure of a database. Like Twitter going from 140 characters to 280, they had to change the structure of a database. It was kind of a big deal. Yeah. It's not like forbidden, it's not huge, but it could have unintended cascading changes across the rest of your data stack, right? Cool. Let's see. So something I didn't really cover with y'all is a concept of a foreign key, and I'm going to bring this up a little bit. We saw the yeah, here we go. On the salaries table, I showed y'all that we have a constraint where the employee, if we're recording a new salary, the employee number has to exist on the employees table. This is something called, so the primary key of the salaries is the combination of employee number and from date. So its unique identifier is this composite, right? But when we are on a given table, like salaries, for instance, and we're referencing a column that we have in common with another table, it'll be called a foreign key. A foreign key. So to put it another way, a table with a primary key is its unique identifier. If that table is referencing another table's key, that other table's key will be called a foreign key because it's a different table. It's a foreign table, right? And we see this on the salaries, right? Because salary employee number is not the primary. The combination of employee number and from date, that composite, is the primary key. But when we see employee number here, EMPNO, we're referencing EMPNO on the employees database. And we'll see this concept of a foreign key over and over and over. And I'm getting a little ahead of myself because it's not technically in this lesson. But as part of the exercises, you'll start to see some of the linkages as you start exploring the employees database and some of the other databases in here. So let's take a look at our exercises. Open up SQL Pro, okay. Save your work in a file named table exercises.sql, right? Whether if you do file, save query, and specify that, or you write your queries, copy it, paste it into VS Code, save it, that whatever gets the job done. You'll be using the employees database, list all your tables. So you're going to go through these different commands, explore that employees table. What do you like? Be methodical about it. See what you can learn from that. And in the exercises here, you're writing the SQL that it takes to do these tasks, right? These numbers 6, 7, and 8, these are kind of think pieces. So you don't need to write code for 6, 7, and 8, but rather maybe comments, right? I would imagine that salary has a numeric type, most likely, right? So go through these. I want you all to really explore at this part of the game. It's coming on 4 o'clock or so. In the exercises here, really get to know the linkages and the structure, and check out this relations as well. This relations area. I want y'all to explore that a little bit. Cool. So folks, that is the tables lesson. I'm going to stop my recording.